Hey everyone, we're back with the whiteboard session with Greg here. My name is Chris Kim. I'm a developer relations engineer at Aptos Labs. Greg, you want to introduce yourself?
My name is Greg. I'm the head of developer relations at Aptos Labs. I've been around for forever, and this is why Chris asked me all the hard questions.
Exactly. So I'm the newbie here asking this guy all the hard questions, and so that hopefully one day I can become like this guy and know everything about Aptos.
You already like me, don't worry.
All right, so today we're going to talk about storages on Aptos. So just the reason why I wanted to cover this topic was because when people come to Aptos and they want to start building applications, they need to understand like the structure of storages on the blockchain, on the Aptos blockchain. So let's start there. Can we kind of quickly talk about the storage structure on Aptos? Maybe draw a diagram to kind of help understand?
Yeah, so you bring up a good point. Storage is probably the most important thing in the blockchain, especially because when we think about charging gas for transactions, there are two parts. There's storage and there's execution. And generally, storage is much more expensive than the execution.
Yeah.
So the way that storage works on Aptos is that Aptos is really focused around this logical tree of storage. Well, you have an address, say 0x1 for short. And within that address, you'll have multiple resources that are associated with it.
Okay.
So I might have a resource called account. I may have a resource called Chris is awesome. And inside these, there may be some data. So in the account, there's sequence number, and then like auth key, and more data there.
Right.
Versus like maybe equals true. Right. Okay. I try to be funny.
This should be a fixed value, by the way. It shouldn't be.
It should change. That's why I put maybe, because if I change it to false, it's maybe
awesome.
Maybe you are awesome.
All right, okay.
Maybe that means you are awesome. It's just not you're not maybe awesome. Okay.
Sure.
Anyways, so the way that we have it is a forest of different resources. Each of these are stored logically as a separate hash of data. So the way that storage lookup works is you take the address, you take the name of the resource, and you hash those together, and you get some key into storage, and it gives you this resource here.
I see.
This box that we have here is what we call a storage slot.
Storage slot. Okay.
So a storage slot is actually what you are charged for most in storage. The storage slot is a fixed cost because it's essentially a single value in the giant hash table of storage.
Gotcha.
Okay, so the more slots you use, the more it costs.
Okay.
Additionally, with the changes that we made in some AIP that I can't remember off the top of my head, we added storage refunds.
Yes.
So when we first launched, you just got charged for this, then you lost the money forever. But what we added is you pay a fixed amount for this slot. And let's say you delete the resource, you get rid of everything in it, you get the funds back from that. Purpose here is to make sure that people free space and that they have a reason to do it, because that is a fixed resource. There's only so much storage in theory in space. Otherwise, you have exabytes of data on the blockchain.
Yeah.
Okay.
Quick question. So these resources take up each storage slot in the giant hash table. Does the account take up a storage slot?
So the concept of an account is a little bit interesting. So an address is a location in storage.
It's a location.
Okay.
I see.
And that's, the funny thing is, like, I think this is a thing that all across blockchain has been too pervasive, is that we use these very technical terms and then we throw them at people and say, you need to know how all of this means, what all of this means, right? Like your Ethereum address, you're like, why does everyone have an Ethereum address? It's very confusing to the average user, but what it is it's a hash address. So you take that value and you hash it with some other value to get some other storage.
I see.
So in this case, in order to have multiple slots for each address, we hash the address and the resource name to create it.
And this determines where that hash gets stored in this giant hash table.
Yeah.
Gotcha.
But I mean, they're hashed, so it
Yeah.
doesn't really determine where it is, it just determines how you find it.
Right.
We'll get into that later too, because this hash of these two values actually gets used for other purposes that aren't just resources. And we'll get to that later. We'll get to about tables, which actually create their own hashes that go into the same name. They have a different separator, but they technically go into the same giant table.
Cool.
Yeah. So that's pretty much the simple part about this. Each storage slot is in this forest that keeps track of all the resources.
Yeah.
This makes no difference. As you can see, I said address, whether it's an object or an account or any other item that we want to call it. Each of these slots are the same.
I remember seeing on the dev doc that there are 3 types of accounts on Aptos. And one is just a normal account that users use. One is an object. What's the other one?
Resource account.
Resource account.
Okay, so
Okay, what's that?
there's a lot of misnomer. So the problem is account is a really overloaded word.
Yeah, it is.
That's why I went back to address, because I was about to say account here. Objects technically aren't accounts, but they can be accounts.
Yeah.
The definition of an account on Aptos is that it has this resource that says 0x1 account. What that means is you can sign as that address with this authorization key and with this sequence number. Okay? So that's the one specific thing that's used for.
Okay.
An authorization key is a hash of your public key with some identifier of what type of key it is.
Okay.
That way you can have your Ethereum style ECDSA key, you can have ED25519 key, whatever, or like keyless, all that stuff, you can have in one namespace but have different types of keys.
Yeah.
You can actually rotate between them, but that's a whole different story. Now, resource accounts were something that we created early on at Aptos.
Okay.
Because objects didn't exist. So what a resource account is, if I were to create another address, I programmatically can create an address, 0x123. This would be random, obviously. And it has an account in it, again. But it also has another resource called resource account, or something like that. I honestly can't remember. This has I think there's an owner or a signer, no, it's a signer capability. Signer cap. So what this signer capability says is, if you have this signer capability, you can access the signer for this account, for this address.
Okay.
Okay. Stick with me. What a signer does is it allows you to authorize for an address.
Yes.
Okay. In the original accounts, your signer is generated through the VM, through your authorization key, in your account. So that means only if you have the public key that maps to that address can use it. But that means that whenever you want to submit a transaction, or you want to access something in the storage, you need that key to sign it.
Yeah.
So think about things like an NFT mint. But that is a simple example. NFT mint. If I want to mint for a collection, and I need the minter to sign every transaction, that slows down the minting significantly, because I go to your server, you tell me, and I sign a transaction that gives you the NFT.
Right.
But then it means either you have to pay them ahead of time, and it gets through this other stuff, and it means you're serialized, where every transaction goes through that one server or that one person. So instead, what you can do is you create a resource account. You can programmatically get the signer cap. So instead, this owns a collection. So then when someone else calls the transaction, you can access both the original user and the collections owner. The user can send you money, and then the contract can actually go and sign the transaction, sign the part that requires you to create the NFT and mint it and give it to you all in one transaction.
Okay.
Okay. And this is what people would mostly think about on Ethereum as a contract address. So this was the closest thing to a contract address that exists today. You can put storage in it because it's a normal account. You can go and write a contract and put it on there. You can do everything autonomously there. without necessarily needing other people to do anything.
I see. Okay. So who owns this resource? This is a resource, right? The resource account itself is a resource?
There's a resource for the resource account, which contains this signer capability, or it might just be called signer capability. I can't remember.
Right.
But what this signer capability does is it basically lets you create the signer for this address.
Okay.
So you can take this and you can store it somewhere else. I can store it in this account if I want. And then, or I can even store an account that lets me programmatically let other people access it.
This might be another whiteboard session.
And this is why, and generally, unless you're an Ethereum developer, I personally don't like resource accounts. They're a little confusing. It's very much more akin to what people think about from Ethereum, where you create an account, the account has a contract address, has all the stuff in it, and you can access it there. But it's a little awkward how you access this, and I don't really want to go into explaining it today.
Okay.
But from that standpoint, you can go create an account, you can lock down the contracts so no one can change it, and just access a bunch of memory there.
Cool. Yeah, for today, let's just leave it at there. Maybe we can talk about this more in depth later, because the 3 different types of accounts. On Aptos.
We can go to the third one because
objects, right?
I actually think the third one is better to replace this one because this is a bit messy. So,
excuse me.
And I can talk all day about objects because there's a bunch of other stuff, but we're going to keep this simple.
Cool.
So the third type is objects. So you have a resource and object called object core. It doesn't necessarily need an account resource unless you want to sign as it. There's some details there that really don't matter. So you have object core. And then in the object core, it has an owner and is transferable, and then some other data.
Yeah.
Okay. So the way that the objects work is that it has an owner. So the owner would be, say, this account. It's just an address here of this value. So we draw it as a pointer, but it's just the value of an address.
Yeah.
And that means you have very easy authorization based on an ownership of this address, essentially. Then you can also do things like transfer it. This can have other resources underneath it, and so on. Makes it really easy to be able to have a bunch of different resources in what we like an object, a group that are related, associated in that way.
Yeah.
There are some other specific details about storage that come with objects, where you can do certain things that make it a little bit more efficient in storage.
Okay.
I don't know if we want to get into that right now.
Before we hit there, let's just kind of do a quick recap of what we just talked about. So there are 3 different types of accounts: resource account, object, and just normal account. And all of these resources are where all these storages are going into. And these resources are tied to these accounts as a tree shape. And they're just a bunch of accounts on the global storage of Aptos blockchain. So that's the TLDR of the storage structure on Aptos, right?
Yeah.
Got it. Okay. I think having that understanding is really important as a developer, because when you're writing a move module and you're creating a bunch of structs and you want to store certain data, it's important to understand where that data is being stored and who owns that data. Well, here let's use the term resource, right? Who owns that resource? And so, yeah, that's good.
That's a good summary.
Yeah, good summary. Cool. Now let's dive into what you were going to talk about, the objects, all the resources that are stored in an object. Yeah.
Yeah, we can do objects, and then we'll get to tables afterwards, which is the other fun storage thing.
Sounds good.
Okay, so objects are one AIP, one Aptos improvement proposal about talking about how we can change the way that storage works in Aptos.
Yes.
But there's another one that's associated with it called resource groups.
Okay.
So resource groups are AIP that basically lets you combine a bunch of different resources into a single storage slot. So as I remember, I told you with the resources in a address, each one is a storage slot. Each one of those has a fixed cost that's associated with it. So one of the things that we added was with resource groups, you can store it in a B tree, or of resources within one storage slot. Okay? Because imagine I have this resource and it has one number in it. It's probably not great to have it take an entire storage slot
it's a
itself.
waste of slot.
Yeah. This is very common, by the way, like through a lot of program, like people program lots of stuff like that.
Of course.
So instead what we do is Object Core uses this group called 0x1 objects group.
The object core?
Yeah, so objects use this. So
Objects use this, okay.
there's this annotation that I'm not going to write it on here because it's long. This was already long enough. Object group is a group, is the name of a resource group being used specifically for objects. So object core is in this group, and then ideally, in most cases, you want every other resource to be in that object group that is in the object. Okay.
Okay.
It provides some caveats and trade-offs that come with it, but it usually provides better performance from the cost perspective of storage.
Right.
Okay. So now let's say I want to have another resource. We're going to say it's sticky notes or something.
Sure.
Okay, and this has like a vector of notes or something.
And this is a resource stored in this object.
This is a resource stored in this object.
Okay.
So let's say I make this resource that's called sticky notes, and I want to put it in this object group. Now, when I see storage, here's a single slot, and then there will be the object core, and then sticky notes in this B tree. So now it's stuck all in one slot, so I don't pay the extra cost for multiple slots,
Yep.
but I still get all the same data that I want in it.
Okay.
There's a bit of a trade-off here because the more resources I add, the longer it gets in the B tree. Okay, and every time I load a storage slot, I load everything in the storage slot. So if I put too much stuff in the storage slot, it can get really expensive.
Every time you try to use it.
Every time you try to read, but it is a lot more efficient with how much space you have. I haven't seen in really most cases where people usually end up running into these kinds of issues unless you're at huge scale. So I generally suggest just putting them in here because usually you don't have too much data that you're putting along. So then, right, you can have more things here. It's a fully ordered tree. So it's an n log n, or sorry, it's log n lookup
Okay.
to find a new resource whenever you add more resources to it. But it loads all of them at once, so that way, if you do load the object core and sticky notes in the same function, it's going to be faster. Or faster, but obviously because it's faster, we charge less than gas.
I see.
And how that comes down to is like, you know, most of the time with an object, you want to know who the owner is. And then you want to go and do something with it. So it makes sense to load them at the same time because I say, authorize that the owner of the resource, of the object, and then let me go and modify something in the sticky notes.
Ah, I see. That makes sense. That makes a lot of sense.
Yeah.
Okay. But if the B tree gets too big, you said it's just a log of n, so
Yeah,
that,
I mean,
that would make it slower, I guess.
And make it slower. I mean, generally that kind of performance doesn't really end up being a problem for you. It just becomes like gas costs. Okay.
Would it become more expensive?
It would become more expensive in the execution costs rather than the I/O costs.
I see.
But it also, if it's too big, the I/O cost is a lot. Now, like I said, not all. Well, very few times do I see anyone actually put too much stuff in here. So that's just a trade-off that you might want to do if you make something really complicated or whatever it comes through. But just something to keep in mind.
Okay, that makes sense. So just to clarify, when you group all these resources in a resource group, if you want to look up one of them, you have to look up everything.
Yes. So it's a good point there. Whenever you see the actual transaction output, it will show all of these in the right set.
Interesting.
All of them. So keep that in mind. Like sometimes it gets really large. But that means it's really nice because then when you change the object like owner, you have the information about the resource. So it makes it sometimes easier to index in that way.
I see.
Because like, let's say I transferred my NFT to you, I see the name of the NFT is in this one. So this is actually like token, which it has the name of the NFT. But then I see the change in the owner at the same time. So now I've transferred to you, I can see this token was transferred to you. The other way is to use events, which I highly suggest instead of doing too much of this traversal, but it does make it simple for some cases.
I see. We will dive into this topic a bit more later on, but I guess based on what I heard, it sounds like if I want to store something that's not looked up too frequently, but like if I just can read it once, maybe store it at an off-chain like cache or something, and then use that on like the front end, in those type of use cases, this sounds like a great deal because you just have to look it up once, get all the information, just store it somewhere else, and then use that data to populate something on your front end.
Yeah, yeah. And if you're getting something off it and you're not using it on chain, I wouldn't put it on chain too, in case unless you need permanent storage associated with it.
True.
Or you end up using something like Shelby for that.
That's a different topic right there.
Okay.
Okay, that makes a lot of sense. Now, one question though. Why is this only possible for objects and not for...
So you can actually create your own resource groups, but keep in mind, anytime you create a different resource group, it's a different group entirely. So I could actually have an object and have 3 or 4 different groups, but it's sort of a buyer beware, create your own resource groups because nothing else is using it. So the only thing that can take advantage of it is your contract, versus objects are shared, so you actually can take advantage of that by multiple people's contracts. So like, for example, NFTs. NFTs use the object group. So I make an NFT and I want to add my own custom stuff on the NFT. It'll all be in the same slot.
Yeah. Okay.
Because I'm using the existing group.
So let's say I create a resource group where that resource group is stored in not an object, but just a normal account. You're saying that's possible?
Yeah, you can also store things in object group in a normal account. There's nothing stopping you. What this is essentially is a tag for a slot. So it's right now, before I told you, right, there's an address, and then there's a resource name, and that pairing gives you a slot.
Yeah.
This is your resource name. So now the object group is a slot name. And then you're just putting sub-slots
I see.
in it. These ones don't cost you storage costs. The big one does. So you can create your own ones. It's just you take more advantage by using this one because you don't pay for an extra slot.
Got it.
Yeah.
Makes sense.
And I say buyer beware because it's really easy to... Once you start using that slot, you won't have to keep it. So you can't like get rid of it unless you create new structs and rewrite your contract. And because of the way that the blockchain is built so that it prevents it's backwards compatible,
Yeah.
Once you've created a struct that is attached to a resource group, you can't get rid of it.
Makes sense.
Yeah.
Cool. All right, now let's talk about tables. You say you wanted to cover tables.
Yeah, so we talked about how account storage works, how objects work. So now we're going to talk about tables, which is I would say like the third type of storage.
Okay.
The third type of base layer storage, because technically resources and resource groups are the first two.
Okay.
So tables are third. And this helps build upon all the other types that are associated with smart tables, maps, etc. All use both.
Got it.
So we talked about how there's an address and there's a resource name. And these are hashed together to make some key in global storage. Okay. What a table does is it lets you create a key without an address and a resource. So instead you have a table which has a key and then a value. Okay. This is a raw type in move.
Okay.
This key can be almost any value. Okay. But I believe it has to be of a struct of a key type.
Okay.
Okay. So the way that this works is it takes this key, it hashes it with there's some identifier. There's technically some other identifier that's hashed with these to namespace them. And then that gives you a different hash key. So these are, because storage is a giant hash table. So this maybe leads here, and then I have a table of key and value. So let's say I have a table of U64 and note.
Note here is a struct.
This is a struct. I guess it could be anything. Let's make it string.
Sure.
I highly suggest, if you store stuff in tables, to use structs and use more than just one item, and we'll get to why.
Okay.
So, yep, like let's say I have 0, 1, 2. 0 might map to this slot. 1 might map to this slot.
Oh.
2 might map to this slot. This is global storage. These are the slots I told you about that cost per slot.
Oh, so it's not one table, one slot. It's one value in table, one slot.
Yes. So this is why I highly suggest you use a resource. I'm not a resource, a struct here, because if you're storing a string here, it's like storing a small resource and paying the cost.
Yeah.
So there are some trade-offs that come with it. This is the base level system that you can use for this.
Uh-huh.
And this is nice because, like I've hashed into a table, I have some values. This is an O1 lookup, right? So I don't have to go and iterate through anything to find it. So the execution time is low.
Yeah.
But the storage cost is high because I'm paying for each slot. And I forget, you might not be able to you can't fully delete a table. So you don't get all the money back.
Oh, you can't delete it?
I think you can delete the rows, but you can't get rid of this
table
thing that's holding it.
I see.
So buyer beware when it comes with it. Once again, all these things are trade-offs. So the way that this table lets you put stuff into space, you have a single item in each one of those, which is fine if you want to store a lot of data. It's also fine. Originally, when we first launched the blockchain, people used it for whitelisting NFT projects.
Makes sense.
And the reason why is because they had like 10,000, I don't know how people can do like 10,000, 100,000 people on the whitelist. This scales infinitely, right? Because it's using a hash of it across the entire storage space. But if you but smaller amounts, or smaller structures don't work very well. All right, so we've talked about this. We have a table, but why do I use this table instead of, say, a vector? A much more simple type.
Well, the vector, you gotta iterate through to get all the values, right?
That's right, but if I'm using a table of U64, what's the difference between 0, 1, 2, 3, 4, 5, instant lookup in the table, and in the vector, or the table?
Okay.
Okay, so this is actually a good example. So let's say I have a vector address, the whitelist, versus a table U64 address. Actually, no, I'm doing the whitelist backwards.
Right.
Vector, so instead of an address, we will make this, we call simple map, and I'll get into what a simple map is in a bit, of address U64, or actually, no one's gonna mint that many, U8. And then this is address U8. Okay. So a simple map is a vector. It's the worst, it's the least performance data structure whatsoever.
Okay.
Because it's what is a vector of what is essentially a combination of address and U8. Kind of.
That's what simple map is?
That's what simple map is.
Okay.
And it's particularly really bad because someone didn't even think about making ordering or anything. So what it does is, this is like your entry to CS class map.
Okay.
Insert is O1. Okay. Lookup is O of N. Removal, similarly. The reason being is I have my list. I add 1, or it's 0x1 and then like 5.
Sure.
0x10, 2, whatever.
Yeah.
0x0, 0. So if I want to look up 0x0, I have to go through the whole list. It's not ideal. But, if you only have like 10 things in the list or 20 things in the list, it's the most efficient because it's just a vector, right?
I see.
So there's a very good trade-off there where if I really don't have that many things, it doesn't matter, it's really simple in the space, and I don't have to think about it.
Yeah.
But it's like the least efficient. Storage-wise, it's fine. The problem is I would say if you have more than 20 items in this list, do not use the map, simple map. Because you're going to have, you can use up to probably like 100, but once you start doing that, now you're doing 100 lookups every time you want to do something.
Yeah.
It's not particularly great. You could do something similar here if you knew if these were numbers instead in the first place, and you make it a vector and you just jump index to those.
Oh, you can jump to the index? Oh, well, yeah.
This is an array or a vector, so you can just go straight to it.
All right.
But that never happens. Like, the cases that usually you want some address associated with it, some
you
more
want just directly look up the
complicated
address.
data. Someone who wants to hack like really efficient data structures, they can figure that out. Because you could also do things like do a hash and then do something with it on there, but it's a lot.
Just a quick question. For a simple map takes up one storage slot?
No. This takes up no storage slot, but you put it into a resource which takes up the storage slot.
I see. Okay. And can the simple map hold other structs?
Yes.
Oh, it can.
It can. They just need. It needs either store or key. I can't remember which one for each one. Oh, and they both need store. So this and this need store. Store is the property that says you can put another struct.
In structs.
This one might need key. I can't remember. Actually, no, it doesn't. I think it might need copy. You might need to be able to copy the key or something like that, but otherwise it's pretty much just store whatever you want.
Okay, so it sounds like simple map it's cheap for storage cost, but expensive for
lookup and usage and everything. So don't use that. Unless if you're playing around with something, you can use that, but I highly suggest you don't use it. It also doesn't provide a very good iteration mechanism. It kind of sucks. I would use ordered map.
No, there's
instead.
a different map.
I know, right? And then I can do address U8. Ordered map I think it's a B tree.
Okay.
So that means insert is O of log n. Same with lookup. Removal. Removal might be, it's probably more because you have to shift the tree around. But that makes it a lot easier, much more consistent, rather than everything being here, lookup and removal is O of n.
So it's more scalable.
It scales better. And then also it's ordered, so like you can get an ordered list out of it.
And so when you say order, do you mean like the order of things stored in the order map? Like how should I say it? Like the simple map, is it unordered? Meaning like
yes.
Every time you look it up, the order changes?
So what I would call it is simple map is stable, where it doesn't change the order. Okay. But it's not sorted.
Oh, I see.
Ordered map is sorted because it's a B tree.
I see.
Every time you insert into a B tree, it sorts.
Yeah, makes sense.
And a vector is not sorted as well. So that is the nice thing is the ordered map is sorted, simple map is not, and that makes it a lot easier for you to do all kinds of other things.
Got it. Makes sense.
Yeah. And then I think you can actually like iterate through it versus the simple map. There's no proper iterator. It's kind of awkward.
So like in most cases, unless you really want to get technical and detailed, just use order map.
Yeah, just use the order map.
Yeah.
But there's a limit here. Okay, so the vectors don't work well. I think they don't work great after about 1,000 or 10,000 items in them.
Okay.
Especially if you want to iterate through them, right? You go through 10,000 things, you're doing 10,000 actions, and 10,000 actions of moving plus 10,000 comparisons plus whatever, your gas starts to add up. But for the whitelist solution here, log n isn't too bad for order map, but I believe there is some limit to the amount of data that you can store in a vector. this is backed with a vector, so there's some limit. If you have 100,000 of them, don't put it in here. So instead what you do is you use a table.
Okay.
So a table lets you store a lot larger amount because each address just has a single value. But, now I said, this costs you 1 storage slot, this costs you n storage slots.
Yeah.
Which
Big
is-
trade-off.
And if you look at the gas costs on Aptos, the storage cost is higher than the execution cost by quite an amount.
I see.
And that's because storage is a much more limited resource than execution.
Of course.
Because we have such a great, parallelized and fast system that is much cheaper.
Right.
So, because I have this, I just can simply do a O(n) lookup, insertion, etc. What I can't do with the table, iteration. I can't tell you who everyone's in the table.
You can't get the
No.
entire.
Because it's so much data, right? This is an infinitely large
Right.
data source. You can't get everything out of it. That's why generally when you use a table, you want to use an indexer to keep track of the stuff that's in it.
I see.
So it's a trade-off of how easy it is for you to use on-chain versus off-chain, okay? So listing out everything is usually an off-chain action.
Yes.
Iterating through it, you also don't want to do on-chain because it's going to be too big to do anyways,
Yep.
unless you do some extra tricks, which I'll get into later. So this is just a O(n) lookup and write, read, whatever, but you have to know what the address is you want to use.
I see. So that's where the indexer comes in, and you got to figure out what the key, in this case, address is,
Yeah.
and then use that when you're calling.
Otherwise, you can cheat it. You can make this like a U64, and then it's like 0, 1, 2, 3,
Yeah.
4, 5. But then what happens when you delete one,
Exactly.
right? Things like that. So that's the allow list, whitelist situation is this scales infinitely. And this is what the order map didn't exist back then. So people originally tried to do the simple map. It didn't scale very well. This was the solution at the first launch of Aptos to create the whitelist for everyone.
Got it.
But this is expensive.
Makes sense.
This one doesn't scale to 100,000. So now we see we have vectors, one amount of space I can put it in anything, and then I have a table that is storage slots. So then let me propose to you, how do we make bigger storage data that can extend over a single storage slot?
I don't know.
I know, I tricked you on this one. I didn't even ask you this before. I'm giving you pop quiz. You combine them.
Okay.
Yeah, you're like, I don't know what you're talking
Combine
about. Okay.
them?
Yeah. So I have a table. I have some hash key of some sort. And then I have a vector of the value. Or basically a simple map. I'm going to just
Simple
put,
map.
put an order map here to make it simple to explain. Key val. Okay. So, in order to, I have an order map. It goes from 0 to 100. I want to make it go from 0 to 1,000. What I do is I say 0 through 100 are in this first slot. 0 through 100 through the next slot, etc.
Oh, I see.
And then I order them in that map. So this is actually just a sectioning of the
That makes sense.
map to make it into submaps. So a table of an order map with a key is what we call a big order map, which takes in address and U8. And there's some configurations you make to make it like more efficient or less efficient
I see.
based on the
So
storage.
this would divide up into multiple slots just automatically.
Yeah.
Ah, okay.
Yeah, I mean, there's a configuration to figure it out.
Like
It
how
does-
many-
It does
how
some balancing, but this is a U8. You probably want to store way more things in the slot than the other ones. And then you have, this is the giant table. So one goes here, and then this is an order map. Here's an order map.
That's smart.
Yeah. Though we didn't call this one smart. We called it a big order map.
Call it big.
Okay, so a big order map basically does the same thing as order map, log in lookup, log in everything, but it's across multiple slots. And there's some nuances there. You can list some of them. You can't get the entire list because it's way too big, but you can iterate over some parts.
Yeah, it's like a hybrid model. Like,
It's a hybrid
you
model.
know, it's a cheaper way to store a lot of things. You kind of get the best of both worlds, but it's not the greatest of the both
Yeah,
worlds.
it's still like, if you want something to be cheaper, like if you know that you're only going to store 100 things, do not use this, right? If you want to, if you know like you may have tens of thousands of things, you should be using something like this instead.
This is really good. I'm glad we're talking about this because I think smart contract development surprisingly is very close to like low-level coding, like because you're working with.
It is low-level coding.
It is, right?
You're writing on a VM. Technically, this move is like compiled straight into bytecode and assembly, so it's very much that low-level programming.
And you really gotta think about how to optimize, your cost and where you're storing things. So.
Yeah, and like when I ask someone a coding interview question, I ask them like, or I expect them to do estimations of like the amount of space they're going to need and all that. Those are the things that come into a system design question, which is when you make these decisions. How do you decide you want one data storage versus the other? Very important for any software job.
Yeah.
So there's one more type that we can talk about, smart table.
Oh, now the smart one comes in.
Which is not so smart.
Okay.
So it also has like a hash key, but then it has, I think, something similar to like a simple map, or it might be semi-ordered, but I'm just going to say it's a simple map here for now.
Okay.
So I hash the keys and I send them to different parts, and then I iterate through that vector or simple map to find the key that I want.
Okay.
Okay. The problem there is if you don't control all of the keys that can go into the smart table, there's an attack vector. And you're probably like, what are you talking about? This is a hash of whatever the input key is.
Right.
Someone's smart enough, they want to break your contract. So they figure out how to get the same key for each one, and they make this list really long. Really, really, really long. Breaks it.
Why?
Because then I try to look up something in this list, and it comes the same problem in the first place. I got 10,000 items in this list. I'd iterate through the whole list, and then I run out of gas, or I hit some execution limit, or hit some storage limit, or whatever. So that's why the smart table is not so smart if an outside person can control this value.
Oh. So smart table doesn't automatically divide it into different slots like the big order map?
It does. It does a hash of the input. But the thing is, the ordered map is, because it's ordered, you can figure out which slot, you can separate the slots a lot easier and then distribute it more evenly. And then the other thing is, I believe it has some rebalancing in there where it takes ones from one slot and puts in the other if it goes over some limit.
Okay.
So, and because that would be like instead of being O1 insertion, it would be O2, like an extra move. So it's not that bad. You just pull one off either end and move it.
Okay. Then what's good about smart table? This doesn't sound too good.
What's good about it is it's essentially the first foray into making your, what we call a bucket table, the ability to bucket items into a hash table. It's okay. It's easy to use for certain cases. It was our first major non-primitive data structure, so it's actually used in a lot of different places.
But what problem does smart table solve that
Big order map doesn't?
Or the primitive table type?
Well, so remember I told you that this creates a storage slot for every single one. For every single,
but this is more efficient in that it's grouping.
Because the lookups here are whatever the length of the map is, which is different. So it's usually O of 1 amortized to something short, but you get more storage efficiency.
Okay, I'm still not clear on what's so different from big order map then.
The difference is the big order map is ordered.
And so this is not.
This is not. So because it's not ordered, it causes some other fun things associated with it.
Okay, it sounds like big order map is the winner here.
The big order map is the winner, but like if you have if you have less than like 10,000 items, use the order map. You have more than 10,000 items, use the big order map. If you think you can get more than 10,000 items, you probably have to use the big order map. Okay? Just keep that in mind whenever you're scaling something. Now, if you're creating something every time someone uses your website and you're going to do that forever, you probably should use the big order map.
Okay.
Yeah.
How about Smart Table? When do you use it?
I would not use it if you don't have to.
Really?
Yeah.
Okay.
There's some quirks and different things that come with it. So, like particularly someone was just talking to me yesterday. The right set of the big order map shows the full first slot of the big order map on every write, because I think it stores a vector where the order map handle is.
Okay.
But Smart Table, there's nothing stored there. So it's always in a different part of the write set. So it's a smaller output of the whole thing, but it's harder to read.
I see.
That's, I think, the only trade-off I saw.
Okay.
Otherwise, I don't think there was anything else that I remember. Smart Table also has length. Big order map and Smart Table have the full length. Table does not. So you don't know how many things are in the table, even with that. And then this you can iterate with, too.
Ah, you can.
But once again, I would use the big order map unless there's either some particular reason that you find that you like the Smart Table better, and I would highly encourage you only if you control the inputs.
I see. So this shouldn't be like a publicly accessible data storage.
Well, it can be. It's just it's a trade-off, right? If it's going to break your whole flow because of it, maybe you should think about it twice. But we didn't have big order maps at one point, so Smart Tables were actually the only option you would make that weren't so as expensive as tables.
So big order map came last.
Yeah, it was last 6 to 9 months.
Okay, makes sense.
It's actually one of the innovations built for Decibel and Shelby.
Decibel. Ah, interesting.
Yeah, because it needed an ordered data structure. Similarly, Akania actually made a publicly accessible, I think a red-black tree or some other tree, as a priority queue for their order book.
Nice.
So I think this was basically built for an order book.
Very cool. I really love that the engineers behind Aptos Move really they continuously think about how do we make it easier to store these type of large data sets.
Yeah, I mean, people ask us questions about it all the time about how they can store large things, things that they run into, and we like to hear that feedback and try to do something about it.
I think that the natural question that comes with this is that since we're allowing people to store large data sets, does that bloat the chain? Do we have any problems with storage bloats?
I mean, yeah, there is some amount of bloat that comes with it, but that's what you pay the gas for, right?
True.
So that's why you pay the gas storage fee. It's to discourage people from doing things, and then because there is a storage refund, you get the money back.
Right.
So anytime you get rid of a storage slot, you get the refund.
Yeah.
I think the table storage slots count, the Smart Table storage slots count, the resources count. So I highly suggest that you do delete your storage if you don't need it.
I see.
You get money back. Who doesn't want free money? The one thing I will mention is we have to go back all the way to resource groups.
Okay.
With storage refunds. You're probably, Greg, why resource groups? I told you there's a storage slot. Storage slot has some data in it.
Yes.
I have to remove all the data in the storage slot to get the refund.
Yeah.
Okay. So in a resource group, there are multiple resources in there.
Right.
You have to delete all of them.
All of them.
That means in here your object core, your NFT token, your extra fun thing. When you call object delete, it deletes that.
But it doesn't delete the rest
When
of
you
it.
call token delete, it deletes that.
So you gotta...
Actually, I think token delete deletes both.
Okay.
But then your contract added this.
Aha.
So this lot doesn't go away, so you don't get the money back. So you have to make sure that anytime you make a contract that extends a resource group and you want to be able to delete the object, if you want to be able to delete the object, you need to make a function that deletes this and everything else together.
Okay.
So that way once you delete all these resources, you knock out this entire slot, you get the money back. Then you get your money.
If I delete the object core first, before I delete the resources that are stored in the resource group, can I still access the resources in that group, or?
It can be very hard, right?
I see. So the order is important.
The order is important, and the reason why is object core, usually you have something called an extend ref,
Right.
if you want to delete it. Or if you want to access the signer for the object, you have the extend ref.
Yeah.
You can store this wherever, but if you delete this, you can no longer use this extend ref at the end of the end. So you need to be able to get the extend ref and get the signer first, then delete the object and delete all the other stuff with it.
I see. Very interesting. So when you're writing your move modules, you really want to make sure you think about, is this struct or resource, like, can I remove it sometime down the road? And if I can, then I should make sure I design the module in a way that I get the storage slot feedback.
Exactly.
Makes sense. Makes sense. Very cool. Just a very basic question. To delete a resource, does it have to have the drop ability? Or
No, actually, technically not.
Okay. Because I was kind of confused there, because the drop, it was kind of, I was confused between drop and, yeah.
So you need the drop to delete a struct or the underlying types in it, like the underlying primitives in it.
Uh-huh.
But you don't need drop to remove a resource.
Oh, the resource itself.
So when you write the code, you'll write something like move from
Yes.
address
That removes the resource
then
from the account.
struct,
Yeah.
right?
Right.
This will give me let x equals this.
Yeah.
Struct does not need drop. If I don't do anything with this and the transaction and the function ends, it's going to yell at me that I didn't drop it.
Oh.
Oh, that's not droppable. Okay.
Oh, it's not droppable. Okay.
So what you can do is you can actually say let struct, and you can, we call destructure the structure. So let's say struct has U8, right? Or even more than that, but that's fine. If this is the struct, when I go here, I just say let num equals x, okay? So now I have a value called num, that's a U8.
Yeah.
This is droppable,
That is droppable.
so I can actually drop it. You can actually say it's equal to underscore and just drop it right there on the floor.
Even if I don't have the drop ability.
If you don't have the drop ability on the struct. So what that is telling you is not having the drop ability says you have to explicitly destructure the resource. Oh, sorry, the struct, and then remove the items underneath it yourself.
I see.
The purpose of this is if you don't do this and you have a function that does a move from on someone else's code, they could just drop the struct and lose some stuff underneath it.
Yeah.
But for the type safety here, let's say you had, coin doesn't exist anymore, but coin, if you had a coin in here, you have to go and put this in something by the end of the transaction.
Mm-hmm.
So it prevents you from losing things that you don't necessarily want to lose.
Okay. Okay. That makes sense. Yeah. Got it. And let's say I did move from, removed it from the account. Can I put it back in?
Yeah.
You can
Yeah.
just do move to.
You can do a move to.
Okay.
So you can take it out of one account and put it in another account.
Oh, I see. I see.
It gets really confusing, but you can. Just remember that move from takes an address, move to takes signer.
A signer.
Yeah. And if that other account already has has one of these structs, you'll get a conflict
I see.
because you're moving something into a spot that already has something.
Okay.
So that's the other thing you have to keep in mind. That's why generally I wouldn't suggest you take something from one account and put it in another, because if your function is Chris steals structs and you call it on me and you steal it to your account, then you go steal it from somebody else, then that second one will just fail.
And I feel like if I were going to do something like that, I would just use objects. I feel like that's a better way.
Yeah. Objects make it a lot easier to move around,
Yeah.
ownership of things.
Yeah.
And it gets rid of this, like, that's why it's a lot easier because you don't have to deal with this, like, conflicting thing. But the whole purpose of having this move to, move from, and the global storage like this is that we know that we can guarantee there's only 1 or 0 of any of these resources at that account.
Yep.
Or at that address. Which makes it a lot easier to think about.
Yeah. Makes sense. Cool. Wow. Well, let's do a quick recap of
Okay.
because we talked about it a lot today. We first started with the structure of the storage. Again, simply put, accounts, and each accounts have resources, and that's where the stuff gets stored.
Addresses have resources.
Addresses have resources. Yes, that's correct. And we talked about different types of storages. Like we started from simple map, right? Tables, which are like primitive, move type, and then turns out there's a lot of trade-offs there. So we started adding more things like big ordered maps, smart tables, and we talked about all of the like pros and cons of that, right? Some are great for reading the data stored there, but it has higher storage cost. So I feel like if the developers understand all of this and they understand how their resources are going to be used, now they can kind of optimize their code to make sure that they're not wasting any storage slot and also fees associated with it.
Yeah, my ideal state is that everyone is able to have a reasonable amount of costs associated with it, and that they don't get stuck in a place where their contract just fails because they realize they scaled too short.
Right. Yeah. Well, hopefully today's video really helped you kind of learn about all of this so that you can design your Move modules in the best way possible so that you don't break your application, you don't pay a lot of storage fees, and also don't bloat the chain itself. So we're both being responsible and also making your app better. Right. Well, that being said, I think that's it for today. Thank you, Greg, for going through all this. Honestly, it would have taken me like 3 weeks to like learn all of this if I was just
it took me months to learn it. No, I only learned it over time after trying to write contracts myself. So the way that I learned a lot of this was I built my own contracts. One of the first contracts I wrote was a tic-tac-toe game.
Yeah.
Take a look. And it was taking advantage of vector. So I used a vector for the storage. And then I learned that the simple map existed, but then I was like, oh, this is not what I wanted.
I see.
Especially because tic-tac-toe is just a grid. But being able to then like go from there and add on more stuff, creating NFT projects and things that helped me learn about how the storage worked and the trade-offs based on the cost.
Yeah, that's oftentimes the best way to learn, just to like try to build stuff and break things. And
that's how I learned about this, by accidentally doing the wrong thing and not deleting everything.
Well, I'm just glad that you talked me through it so that I don't have to go through that struggle of running into this issue. All right, well, that being said, thank you so much for watching this video, and we'll come back with another episode.
Thanks, guys.
Bye.